Hello everyone. Today I'm going to explain a very simple circuit which can be used to get a 0 to 9 volt adjustable supply using a 9 volt battery and a simple circuit. This kind of circuit is very old, and 20-30 years back people used to use these kind of circuits a lot, but the utility of such a circuit never vanishes. So I'm going to explain this kind of simple supply, which is an unregulated supply, and in the next video I'm going to show a regulated one. The simple circuit which I'm going to show you and explain is within the box, and with a knob I can adjust the voltage, and it is very simple. And I am going to use a free circuit simulation software called LTspice and to analyze the utility of this circuit. Sometimes we need an adjustable power supply which we can make easily using a 9 volt battery and few more components. Battery power makes it isolated, and we can get pure DC, and we can use a simple circuit, and I'm going to show some analysis using LTspice. There are many uses of a low power DC supply. We can power a low power circuit, we can test analog to digital converter input, and we can use as a DC input to test op-amp circuits, etc. There are two types of circuits we can utilize. One can be a simple adjustable circuit without any regulation, and the other one with regulation. We can get our desired voltage in either cases. With the regulated one, the voltage remains nearly constant under various load conditions within a certain range. Any battery can be represented as a voltage source with an internal resistor connected in series. For instance, a 9 volt battery can be represented as a voltage source of value 9 volt with a resistor like this one. The value of this resistor varies, depends on electrochemical properties of the material inside the battery. Usually newer batteries show lower internal resistance, and the older used batteries show higher resistance due to electrochemical degradation. We can easily find out the internal resistance of a battery. We can use a load resistance of value 10 to 50 ohm in range. We can measure the terminal voltage without the load first. Then we will connect the load as shown and measure the voltage across this terminal. If the voltage is termed as VBAT, we can say VBAT equals 9 minus IL multiplied by Rint. Rint is the internal resistance and IL is the load current. And IL is VBAT, that is the terminal voltage we are measuring, and the RL is the load resistance. So using these two equations, we can find out the internal resistance of the battery. So for small batteries, the internal resistance always limits the nature of loads that we are trying to drive. If we consider that a 9 volt battery has an internal resistance of 5 ohm, we are using variable loads. The higher the current, the higher the voltage drop across the internal resistance. Consequently, less voltage is available at the battery terminal. If we want to get an adjustable voltage using 9 volt battery and a 5 kilo potentiometer like this one, we will get an adjustable voltage. For instance, if we wish to get 5 volt, the potentiometer resistance should be 2.78K on the low side and 2.22K on the high side. However, this simple adjustable source has a big problem. To analyze, we can use an equivalent circuit of the potentiometric voltage source. Without the external load, we are getting 5 volt at this terminal. So we can call this voltage Thevenin's voltage, that is 5 volt, and we can parallel these two resistance, and paralleling these two give us 1.23k, that is called the Thevenin equivalent resistance. So the whole thing can be represented by these two, a voltage source and a resistor in series. So you can see that this source has now very high internal resistance that depends on the potentiometer resistance, and so a very small load connected with this thing, a terminal, very low current will cause serious voltage drop. So of course the situation can be improved by using lower value of the potentiometer. For instance, if we use 100 ohm instead of 5 kilo ohm, of course this will go down, but there will be a huge power loss, power dissipation at this resistor, and this is unnecessary. And also we have to use higher power potentiometer. This slide shows how the voltage varies with the potentiometer. So now if the load is connected, even a very small current draw can significantly drop the voltage. You can see over here, few milliamp, and the voltage go down from 5 volt to 1 volt. Now using a single transistor improves the situation a lot. After the potentiometer, if a transistor is placed, a tiny base current IB increases the emitter current several times, or fair to say hundreds of times, depending on the current gain beta of the transistor. So when a load is connected to the emitter, the amplified current goes to the load, while the voltage drop across the potentiometer remains almost the same due to less loading effect. To analyze, we will divide the circuit and find the Thevenin equivalent circuit of this part. To get 5 volt at the output, we need 5.6 volt at the base of the transistor, because there will always be a voltage drop across the base emitter junction, which is around 0.6 volt. To achieve 5.6 volt, the potentiometer resistance will be 3.1k on the lower side and 1.9k on the high side. The Thevenin's equivalent circuit becomes like this: 5.6 volt source with paralleled two resistances, that is 1.18k. I used an NPN transistor whose minimum current gain beta is 200. Whenever a load is connected, load current IE starts to flow. 200 times less current will flow through the base. We can find the terminal voltage drop for a load using these equations. So this is the photo of the practical circuit. As you can see, the transistor, the potentiometer, the banana plugs, and the 9 volt battery within this chamber. Now varying the load resistance, the load voltage will show this kind of behavior, which is very much similar to that of a battery as shown before. The calculated internal resistance is 0.6 ohm, little higher than the battery internal resistance, which was 5 ohm. Practically I found it to be around 7 ohm. Rather than load current versus load voltage plot, we can plot load resistance versus the load voltage. This plot tells when we use high resistance loads, the voltage almost remains at the set voltage, that is 5 volt. As the resistance becomes lower and lower, voltage goes lower and lower. This very simple circuit can easily be analyzed using the circuit simulation app called LTspice. You can download it for free and it is easy to use. With this app, you can analyze very simple circuit and do very complex circuit as well. A brief introduction is given in the video. First, I'm going to simulate a simple potentiometric voltage divider, 9-volt source with 5 ohm internal resistance. R2 and R3 are the potentiometer resistance, and the voltage at this point is 5 volt, and R4 serves as the load resistance, whose value varies from 1 kilo ohm to 100 kilo ohm, and the step size is 1 kilo ohm. As you can see, very small current draw will reduce the voltage a lot. Let us see what the simulation says with our single transistor circuit. In the first simulation, I used a 10 ohm fixed load resistance. The potentiometer is varied, and we will see the effect of load voltage with the potentiometer voltage. As you can see, up to 0.6 volt, there is no output voltage. This is the base emitter junction voltage. After this, the voltage starts to increase linearly following the potentiometer voltage. Keeping the potentiometer voltage at 5.6 volt and varying the load, we can do another simulation. The load is varied from 20 ohm to 1 kilo ohm, and the step size is 10 ohm. As you can see, voltage goes down as the load current increases. It behaves much like the battery. However, the internal resistance is nearly 6 ohm, little higher than the battery internal resistance. With our practical circuit, we found this to be 7 ohm. In the next video, I'll explain regulated power supply, and design and simulation will also be discussed. I'm trying to measure the voltage of a 9-volt battery. You can see the terminal voltage is 9.58. Now I am going to use a load across this battery and measure the voltage again. I'm measuring the voltage, and as you can see, it is nearly 7.5 volt. So from 9.5 volt to 7.5 volt, a drop is there because of the load. Now here is the simple equation. You can find out the internal resistance of the battery. I am connecting a 20 ohm load and voltage is measured 7.5, so the current through the circuit is 7.5 by 20 ohm, that is 0.375 amp, and internal resistance can be calculated by considering the internal voltage drop, that is 2.1 volt, and now internal resistance is 2.1 divided by 0.375 ampere, that is 5.6 ohm. So this is the practical circuit I used with a transistor, a potentiometer, and 9-volt batteries within this chamber. And there is a switch also, and 2 banana plug. So with this potentiometer knob, we can adjust the voltage from 0 to 9 volt. I can use this terminal to connect various loads. Now I am measuring the voltage. This is a open circuit voltage. I mean, no load is connected. So maximum voltage you can see that close to 9 volt. I'll adjust it to 5 volt and connect a load. It is now 5 volt, close to 5 volt. Now I am connecting the same 20 ohm load across this terminal and see the voltage. As you can see, it is dropped to 3.5 volt. Now I'm going to use the simulation software called LTspice to simulate the circuit. So I'm using a new schematic using the button, and here is the circuit. That is a 9 volt battery, and it has an internal resistance of 5 ohm, and with a source of 9 volt, this battery will be used to simulate all other circuits. So first click this button and I'll get the source, voltage source. And then the various resistors. This is the internal resistance, and these two resistors represent the potentiometer. And always there should be a ground terminal to have 0 voltage reference. Now the circuit is complete. This one is the simple potentiometric voltage divider without the transistor. So you can see the R1, the internal resistance is 5 ohm. R2, I am putting some values, 2.22k. And the lower one, R3, is 2.78k. So combining these two, we get 5 kilo ohm. That is the value of the potentiometer. Now if I simulate, there are several simulation types: transient, AC, DC. So I am using transient. So you can see transient 0 to 1 second simulation. Now if I click the run button and click the point here, I'll get the voltage. You can see 4.99, almost 5 volt is there at the terminal. And now I'm going to add a load resistance here and see what happens. So in place of load, variable load, I will write VAL within curly braces so that we can vary the load and see the effect. And then dot op, dot command, dot set step parameter, P param, and val, that is the value which I am going to vary, and 1000 to 100,000, that is 1 kilo to 100 kilo, and a step is 1000. So now I am going to simulate this thing. So if you start the run button, you can see there are so many steps. These are voltage steps shown, and it is not very good way of looking that. So I am going to change the horizontal scale. Instead of time, I'll use current through the load resistance R4. And let's see what happens. So time I am replacing with IR4. R4 should be in bracket, and then click OK. And then if I start simulating again, I'll get the current through the load and voltage across the load. But now I am going to use also the marker points. You can see all the points are shown there. As the current goes up and up and the voltage goes down, and very little current can cause serious voltage drop. So that's why this kind of simple circuit is not a very good choice. So now I'm going to add a transistor and simulate this same, the potentiometer, the transistor, and a load. Load is varied. And let us see what happens if I do the same simulation, but the load this time varies from 20 ohm to 1000 ohm. And you can see that the voltage drops, but at much higher current. So the internal resistance is lower now, close to that of, compared to that of a battery, that is close to 5 ohm.